So we're going to continue our look at some of the large-scale atmospheric processes and look at tropical climatology. So we're going to focus on monsoons and cyclones. Now, if you remember when we looked at the general circulation of the atmosphere and that three-cell model, we started off by saying that the intense heating at the equator created that uplift that then spread out and then sank down at around 30 degrees north and south of the equator. That was our Hadley cell. Created that circulation, that convection cell, large-scale convection cell around the equator. So on the ground surface at the equator, you have air rushing in from north and south. Now, where that air collides, we call that the Intertropical Convergence Zone, or ITZZ for short. So those locations around the equator, where you get that intense heating, that high levels of evaporation and rising air, that produces intense rainfall. And we call the rainfall that is associated with this intertropical convergence zone the monsoons, and you've probably heard of that. And you can see that band of monsoons in satellite pictures of the Earth, where you get this band of clouds around the equator. That's what we call our intertropical convergence zone. Now, like that model, that three-cell model of general circulation of the atmosphere, those cells moved north and south as the sun moved north and south with the seasons. Well, so does the intertropical convergence zone. So the monsoons are seasonal. So in winter, that intertropical convergence zone, or that belt of monsoons, is over the northern hemisphere, and it's located in our part of the world over around Tibet. And so that part of Asia, and you can see there how it extends east and west of there, would be experiencing those monsoonal rainfall. And as we've seen before, that belt of high pressure systems that is concentrated around 30 degrees north and south rises and is now situated over our northern parts of the continent. And so we have more stable air and drier conditions. As the sun moves south, as summer approaches, then that band of intertropical convergence zone also moves south, brings with it the high amounts of rainfall, and then we get our wet season. You can also have a look at how rainfall changes through the year by looking at this animation, and you can see as we progress from January, so our summer, through our winter, back to summer, you can see how rainfall is high in our summer period, and it dries out in the northern parts of the continent over winter, and then increases again as we approach the wet season. All right, so that's the intertropical convergence zone. So that kind of concludes those three major features associated with those three major cells, the Hadley, the ferrule and the polar cells. Okay, now related to the intertropical convergence zone are cyclones, or hurricanes, or if you're in America, hurricanes, or typhoons. Now, they're intense low pressure systems, and you can see that the different names for the same thing differs depending on where you are in the world, as this map shows. So we're going to talk about tropical cyclones. So tropical cyclones are just powerful versions of normal low pressure cells. Now, they're usually generated at the intertropical convergence zone when it's away from the equator. When the intertropical convergence zone is directly over the equator, or 4 degrees either side, you don't get cyclones forming. And in fact, you never get cyclones occurring at the equator. Can you think about why that would be the case? Remember, Coriolis in a cyclone would be causing that air to spin clockwise in a cyclone in the southern hemisphere, but anti-clockwise in the northern hemisphere. So if you imagine a cyclone in the southern hemisphere spinning, as it reaches the equator, it's going to want to spin back the other way and cancels itself out. And so you never get cyclones crossing the equator. Anyway, what causes a tropical cyclone? Well, first of all, you need warm water around about, or anything above 26 degrees Celsius. And that only occurs near the equator, in this area where you get this more intense heating, so away from 4 degrees either side of the equator, but where you still have enough incoming solar radiation to give you higher sea surface temperatures. Now, the theory is it's not precisely known exactly what initiates tropical cyclones, but the current thinking is that they generally develop from smaller thunderstorms that develop over the ocean, that then coalesce into a larger one, and that coalescing intensifies the updraft that is occurring in these smaller low pressure systems. They combine into a larger low pressure system, and then that sucks up more warm and wet air because they're forming over the ocean. Now, as that air moves high into the atmosphere, because they're low pressure cells, what happens to that humid air? Well, as we've looked at many times before, that humid air will condense and form clouds and water droplets. But what else does that produce? What does that condensation process produce? Can you remember back? We've covered it a couple of times. That latent heat of evaporation that is locked up as that air is lifted, as that moisture is evaporated and then raised up, when it cools, that latent heat of evaporation is released into that system, which then adds more heat, and then that means it's going to rise even more, and then more moisture will condense and release more heat. And it's this feedback effect that puts more heat into these coalescing thunderstorms that make them rise up even further, creating even more intense low pressure, and they rise and rise and rise. Remember, by now we're well above our level of free convection, and so that air, as long as it stays warmer, is going to go higher and higher, and the higher it goes, the more intense low pressure it creates, until eventually we get to the intensity or the lowest air pressure, which gives us an intense cyclone. So combine that then with Coriolis, and that air starts to spin. And as long as there's no high air movements cancelling it out, then that very low air pressure will start to spin. It's intense, so the isobars are close together, and so that air is spinning very, very quickly, and we have a cyclone. Okay, so we've all seen cyclones on the news, so we all know what a cyclone is, or a hurricane. Now, the structure of a cyclone or a hurricane, you've probably got some idea about it. You know that you've probably heard of the eye of a cyclone. Well, the structure of a cyclone consists of the eye wall, and then associated rain bands. In the eye of a hurricane, there is quiet, for just a moment, a yellow sky. Now, the reason it's quiet in the centre of the cyclone is, there's a couple of reasons. One is that it's not spinning, okay? So in the centre of the cyclone, it's just outside in what we call the eye wall, is spinning really, really quickly. But in the centre, because it's spinning around a point, at that point it must be not spinning at all. And so the velocity of the air, in fact, drops very quickly, and so it's actually quite calm in the centre of a cyclone. The other reason is that centre is the most intense low pressure. Now, as the air moves in a low pressure system and that rises up into those forces in the clouds, that centre that's not spinning is still very low pressure, and so you actually got some air falling in from directly above the cyclone, and that gives the impression that air is not moving very fast. It's actually coming down from above, and so it feels very calm. So that air is sinking rather than moving across the surface of the earth, and so we have a more stable appearance in the eye of a hurricane or a cyclone. Now, the yellow sky appearance is interesting. You've probably seen images like this one where some crazy people in aeroplanes fly through the eye, and they get these lovely pictures. blue sky, and that's true, and you can get that appearance on the Earth's surface as well. But that usually occurs only in very large and very intense cyclones that have a very symmetrical appearance. Now, in most cases, these huge storms are not quite so symmetrical, and they'll be a bit messy in the middle. Sure, you'll still get a decrease in wind speed, and you'll have a break in the clouds above you, but it won't be completely blue sky. But what you'll have is lots and lots of humid air in the eye of a hurricane, or if it's moved over land, that uplift in the eye wall is lifting up dust particles as well. And all of that means that any light that's coming in, unless the sun is directly overhead, if the sun is at any angle, means that the light that is coming in is being refracted. And the blue light will be refracted out, leaving the yellow or orange light. Just like at sunset. Why does a sunset look orange and yellow? Because as the sun sets, it's passing through a longer part of the atmosphere, or passing through more atmosphere. The blue light is being refracted out, and so we don't see it, and all we're left with is the yellow light. Well, the same thing happens if you ever happen to find yourself in the eye of a hurricane. You might find yourself with a yellow sky. All right. Tropical cyclone has many features, and I found a very good presentation from the Bureau of Meteorology about cyclones, how they're categorised, and the effects that they can have. So let's just watch that.
The northern coastline of Australia is one of the most cyclone-prone areas of the world. Communities in the region are threatened by tropical cyclones every season, with a very real risk to property and life. A tropical cyclone's effects vary depending on its intensity, so it's important you understand the hazards involved and the potential damage a tropical cyclone can cause. The intensity of tropical cyclones is described according to the numerical scale of 1 to 5, with 5 being the highest rating. These intensity ratings are based on the maximum wind gusts associated with the cyclone, which usually occur around the centre, known as the eye. Tropical cyclones can intensify rapidly. There have even been occasions when a Category 1 cyclone has become a Category 5 within a day. It's essential that your plans to evacuate or take shelter are made well before the predicted arrival of the strongest winds. A Category 1 tropical cyclone has estimated wind gusts up to 125 km per hour. These wind speeds can damage crops, blow over small unsecured objects, and cause boats to drag their moorings. A Category 2 cyclone has estimated gusts between 125 and 164 km per hour. These wind speeds will cause damage to homes, blow over large trees, and make it dangerous to be outside. A Category 3 cyclone has estimated gusts between 165 and 224 km per hour. These destructive wind gusts can rip roofing from buildings, destroy caravans, cause large debris to fly through the air, and the risk of injury is real. If a cyclone reaches Category 3 intensity, it is referred to as a severe tropical cyclone, and is often the point when the characteristic eye of the cyclone will become clear on satellite images. A Category 4 cyclone has estimated gusts between 225 and 279 km per hour. These winds are very destructive, causing significant roofing and structural damage to buildings, dangerous airborne debris, and widespread power failures. A Category 5 cyclone has estimated gusts of 280 km per hour and above. Winds at this speed are extremely dangerous and cause widespread destruction. Along with powerful winds, tropical cyclones can bring heavy rain and storm surge, creating life-threatening situations in addition to the cyclone itself. Heavy rainfall can cause flooding, and it's not always the case that the most intense cyclones bring the heaviest rainfall. Storm surges associated with cyclones can have dangerous and devastating effects on coastal areas, with the level of inundation highly dependent on the tide levels around the time the cyclone crosses the coast. All tropical cyclones are dangerous regardless of their category, so be prepared. Listen to local authorities and stay updated via the Bureau's website. Then you will always have the latest cyclone information.
Okay, And we'll finish our look at tropical cyclones with a look at some real data from the Bureau of Meteorology. This is a page from the Bureau of Meteorology that shows the tracks of tropical cyclones. You can choose from a wide range of years back to 1969. I've just chosen from 2014-15 to 2017-18. And we'll just have a look at a couple in more detail to have a look at their features. The first thing to note, however, is that all of them, without exception, start over the ocean. And that fits because we just looked at what you need to get the formation of a tropical cyclone. They need to form over warm water, and they all do. They, of course, move, and some of them will move over land. So we'll just pick a couple and have a look at what happened to them. So let's just pick this one over here, Cyclone Stan from 2015-16. And if we have a look at the details of it, what we can see is its path, and also what these yellow dots show is the change in air pressure. So up here, it was, it's a bit annoying, move it over that way, there we go. You can see that it started out at 1005 hectopascals, which is low, but not excessively low. And as it developed, you can see how the air pressure drops to 1000 hectopascals, 996, 987. It gets more intense, 980, and then it crosses the coast and is now over the land, and it's 987, 993. So now you can see that it's starting to increase in its air pressure, and that's an indication that the cyclone is becoming less intense. And as it continues on, you can see the air pressure rising even further, and then it dissipates out. Now, two things there. Why does it dissipate? Well, it loses its energy and becomes less intense. Why does it lose its energy? Do you remember what the major driving force or energy source of tropical cyclones is? Well, that's the latent heat of condensation. And so if it's over land, then there's no more humid air available to rise up into the upper atmosphere, and that latent heat of condensation can no longer be released. And so the cyclones dissipate. And we can have a look at another one over here. Let's look at Cyclone Debbie and have a look at its details, and we can see that it starts out in the northern part of, I guess that's the Coral Sea, at 1010 hectopascals, 1008, 1000, and as it moves closer to the coastline, it drops in air pressure, becomes most intense just as it crosses the coastline at 956 hectopascals, and then as it crosses, again, it loses its energy source and starts to increase in air pressure. It does a strange little thing. It heads back towards the coast and perhaps picks up a bit more energy from now being over the ocean, but then eventually dissipates by itself. Okay, so that concludes our look at tropical meteorology.